by my clock, it's 9:15. So we'll just go ahead and get this show on the road. All right. So today we begin the second half of our journey in biochemistry. Up until this point, we've been focusing on the structure-function relationship of different macromolecules. So from learning about buffers to proteins, nucleic acids, carbs, etc. And we capped off that how proteins interact with each other to send signals and how that can manifest itself in a physiological phenotype. And so that's kind of, so the information we talked about with signaling is a bit of a taste of what we're going to be hammering in at the end of the semester with metabolism, when we're going to start talking about regulation of metabolism, which will involve some of the signaling that we talked about in class on Tuesday. So if you really liked signaling, you'll get really excited about the last lecture or two of the semester. So now we're switching from thinking about structure, function, and molecules, thinking about how these macromolecules function in the broader context of the cell. So how do all these proteins and nucleic acids and whatnot in the cell work together to make sure that our body does what it needs to do? And the first part, so today we'll be talking about metabolism and bioenergetics. So we're going to be going tools that our body uses to transfer energy. And this becomes especially important when our body has to catalyze reactions that aren't necessarily favored. Our body has some tricks and some tools to help that happen. That's important because we're going to see those come up with metabolism. Then we're going to talk about glycolysis and gluconeogenesis. This is the portion of our semester, this is the next portion of the semester that will be relatively, that will be fairly memorization heavy. But once we get there, I'll start there on the Thursday, I will walk you through it about exactly what you need to know and why that's important. When we'll talk about after glycolysis, gluconeogenesis, we'll move to the citric acid cycle. We'll look at electron transport as well. Of metabolism, and there's a little bit more in there, but we're going to be covering the steps of metabolism that are associated with our body producing fuel to enable it to keep going and perform all of its bodily functions. All right, so today we're going to start on the basics, or the tools that we need to understand metabolism. By the way, it was mentioned in the free assignment, one of the sections already spent some time on mechanisms when we talked about enzyme mechanisms. We are going to be doing some mechanisms in glycolysis, and in anticipation of this, chapter 13 has a small section on mechanisms. I highly recommend that you take a look and walk through it, even if you are an orgo whiz, just because it brings everything together with these reactions that we would use in glycolysis and with enzyme catalysis, but hopefully a lot of it should be reviewed from what we've already talked about, especially in the review sessions. Okay, so some housekeeping for today. Today we're doing another talking, but we're also going to take breaks to where you're going to be able to work together with your table mates to solve some problems. Again, we're going to be doing, there's a lot of qualitative information in this section, but you're also going to have to learn how to do some calculations. So I'm going to give you the time as a group to work through these calculations. So when you're doing your homework, when you're preparing for the exam, it'll be clearer, and perhaps you'll be able to start with a higher level of base questions than you may have if I just showed you the equation and we moved on. Thursday, we're talking about glycolysis. We also have a quiz. Bearing in mind that you have a quiz that day, and also bearing in mind the nature of glycolysis, this will be a mostly lecture. This will be pretty much a lecture day. And I highly recommend that you start reading through the chapter on glycolysis, but you're not going to be required bearing that in mind. I apologize, I don't apologize, but I guess I do apologize for the inconvenience of moving the review session. I'd originally set it for yesterday from 6:30 to 8:30. Turns out I had some car trouble. It looked like I might have a flat, and so I didn't want to be stuck in Winston-Salem at 8:30 at night, 45 minutes away from my house with a flat. So I decided to move it, handed the car off to Ryan. He's taking care of it today. But with that in mind, I've moved the review session to Wednesday from 6:30 to 8:30 in Salem 013. Again, I don't like having the review session that close to the assessment, but it's consistently when you guys seem to prefer is on a Tuesday. I'll touch base again on Thursday whether when we would think would be appropriate to have our next review session. If we want to do one every week until the exam, I'm okay with that. I will be there. I'm ready to help you and answer questions. I like answering your questions and I enjoy the review sessions, oddly enough. No, not oddly enough. I wouldn't be teaching if I didn't enjoy talking about biochemistry with you. But I think I'll ask again on Thursday because I don't want to come and have an empty room. So think about it over the next few days and see if you benefit from having one next week and one the week of the exam, or if you think we could hold it off and just have one the week of the exam or just 1 2 weeks before. Again, the nucleic acid quiz is in class on Thursday. Does anybody have any questions about the nucleic acid? Yes, Al. Did I say that was fair game? I don't, okay. So here's my thought on that. My thought on that is I would say that's something you would need to know for the exam, but not for the quiz. Yes. So I would say know that pi stacking exists. Know it's important. But I wouldn't expect you to draw it or base stacking. I would be able. You need to be able to draw the bases together. I would also say that you would need to be able to look at the Watson-Crick edges of bases and predict whether or not they would be able to draw that. That's important. I would say that falls under the structure category. I guess did I see another hand? I answered questions. Okay. All right, and that'll be in class on Thursday. If you didn't see, I tried to make it ding when or send you a notification when I put it up. But I posted the nucleic acid quiz from last semester on the side. So if you want to feel a feel for what this might feel like, if you haven't looked at it yet, so I think it's in the practice exams. If it's not in the practice exams, I may have put it in the exams. Go into that folder and find the nucleic acid quiz from last fall, and that should give you a good idea of what to expect for the quiz. All right, and then finally, yes, our exam 3 is on April 11th. We moved it. We'll talk on Thursday about how we'd like to do the review sessions. April, if everything goes according to plan, the content nucleic acid gluconeogenesis will be on exam 3. And I know for most of you, moving the exam back is a welcome change. However, there are a few of you who had potentially that had conflicts that would make taking the exam on April 11th impossible. In that case, my schedule for that week has become clearer, so I'm at a point where I could schedule right where we could talk about that. So if April 11th is a cause of hardship for you, come talk to me after class. All right. Before we move into metabolism and bioenergetics, do we have any questions? I know that the pre-video was relatively straightforward. Okay, so in that case, we will go ahead, we will move on, and we will dive into metabolism. All right, we have the learning objectives here. Have them on your sheets, no need to read them out. So we'll take a really quick minute, and look back at Gibbs free energy. Now, you remember the Gibbs equation from protein folding. And when I talked about protein folding, and I wrote the exercises for you, I really wanted you to think deeply about what delta H and what negative T delta S meant. And we know that delta H concerns the making and breaking of bonds in a molecule. So we thought about the making and breaking of bonds in protein folds, and the delta S corresponds to the order of the system. And so reactions that happen can be driven by either one of these components, but they're working against each other. It's really important. Don't forget that. because it'll come back for the final potentially. But for metabolism, we're not so concerned about the enthalpic and the entropic contributions because what we're mostly concerned about for the sake of metabolism is the delta G, which is the energy that's capable of doing work. So if you have a metabolic reaction that has a negative delta G, that means it's releasing energy into the universe. By releasing that energy into the universe, we're increasing the entropy of the universe, which is favored. But the important thing for metabolism is that by releasing energy, we're releasing energy that can be used elsewhere to do another job that's not favored. And so reactions that have a negative delta G, we consider them to be exergonic. Reactions that have a positive delta G are endergonic, and ultimately reactions that proceed spontaneously towards their products are going to have a negative sign. So if a reaction is going to be favored to form the product, we want to see a negative delta G. And that's not anything new. But throughout metabolism, we're going to be throwing around delta G's like crazy. And so it's good just to set the baseline here. Now, when I gave my touched on this a little bit, but we're going to come back and review it again. So when we're determining whether or not a reaction will proceed, will favor the products or the reactants, we're talking about the free energy or the big G, or the G that doesn't have any superscripts. However, so in order to determine the big delta G or the big G, we have two components. We have the standard state free energy, or the G naught prime. So the naught comes from the standard state, and the prime comes from the biological standard state, because biologists took the standard state set by chemists and physicists and added their own additions to it. And then, which we'll refresh what those conditions are in a second. But then, when reactions are occurring in the cell, they're often not at standard state conditions. So we have to account for this derivation from the standard state with this component here by taking into account the actual temperature and the actual concentrations of our molecule of interest in the cell. So if we have, so for this equation here, so if we're concerned about the free energy change or the free energy for A, so this is the reaction for the free energy of a substance. But when we're thinking about free energy, we're thinking about free energy in terms of a reaction. So if we have a reaction where we have A plus B forms C plus D, the big delta G for that reaction is going to be equal to the standard state free energy change plus R times T times the natural log of the product concentration of the products over the reactant. Now, if the system is at equilibrium, this means that delta G, big delta G, is equal to 0. And so if big delta G is equal to 0, that means if we rearrange this equation, we get that delta G naught prime, or the standard state free energy change, is equal times RT times the natural log or times the natural log of KEQ, of the equilibrium constant. So if the system is at equilibrium, this means the delta G is equal to 0, and that would mean that the standard state free energy change is equal to negative. Take a minute and write in those negatives. Sorry guys, it's second Monday. I apologize for leaving out that negative there. Delta G at equilibrium with delta G, delta G not of the natural log of the equilibrium constant. Now, we've talked a lot about, we've thrown out around a lot of delta G's. Let's take a minute to review, before we go through this, let's take a minute to review our standard state conditions. So under standard state conditions, what this means is that we have 1 molar of each component. We're at 25 degrees Celsius, or 298.15 K, although we often neglect that 0.15, and we're at 1 ATM. Now, turns out in biology, we have to add some additions onto this to make the conditions hospitable for biological reactions. Because it turns out if we have 1 molar of each component, if we're in a reaction that produces a proton, if pH is equal to the negative log of the proton concentration, or 1 molar, I think that comes out to be a pH of 0. Or maybe it's 1, it's a very low concentration. Yes, a pH of 0. If we were to abide by that and we have a reaction where we produce a proton, we have to have 1 molar of proton. That means that we would have to operate a pH of 0, which is a problem for an enzyme to function at a pH of 0. So when biological steady state, or the origin of that prime, we say, okay, we have 1 molar of everything except proton. Proton, we need pH of 7. For enzymes that require magnesium, we have 1 millimolar magnesium. And then we are acting in water as our solvent. So water has a pH of around 56 millimolar. Yes, Grace. Just because there's a lot of bioreactions that use magnesium, especially things that concern nucleic acids, or ATP. A lot of enzymes that use ATP as a cofactor will have magnesium coordinating the phosphates. Okay, so bearing this in mind, so we know that the delta G naught prime, the standard state free energy change, is the free energy change of a reaction that occurs under the biological standard state. This is a value that's going to be inherent to a particular reaction. So in theory, we could go into a book, and for a given chemical reaction, we could figure out, we could look up what the delta G naught prime is and look that up for a specific situation. So one of the things we're going to be really concerned about with metabolism is figuring out whether or not the reaction will proceed spontaneously, or whether it will favor product production, or go back and favor the reactants. And so one of the ways that we can that can give us an idea of which direction the reaction will be favored to go in is by looking at the delta G naught prime, or the standard state free energy. And what this tells us is if we start with 1 molar of everything, and then we allow the reaction to equilibrate or move towards equilibrium, will it have to move towards the products? Will it have to move towards the reactants? Or is it already at equilibrium? And so essentially in this case with the delta G naught prime, it's another way of thinking, of expressing the equilibrium constant. So if assuming that we're at equilibrium, if we have a delta G naught prime that's less than 0, we have to have an equilibrium constant of greater than 1. And so if we have an equilibrium constant of greater than 1, this means that the products will be favored relative to the reactants. So the reaction will have to move towards the products to achieve equilibrium. So if a reaction has a delta G naught prime that's negative, that means the reaction will in theory proceed towards the products. If we have a delta G naught prime that's greater than 0, that means we're going to have an equilibrium constant that's less than 1, that's less than 1. So that means the reactants will be favored. So to reach equilibrium, the reaction would have to move towards the reactants. And finally, if we have delta G naught prime of 0, so delta G is already equal to 0, but if we see, wow, delta G naught prime is also equal to 0, that means nothing has to happen. We're already at equilibrium. Now, so delta G naught prime can give us an idea is what of the driving force behind the reaction. If you have will it proceed towards the product, towards the reaction? However, we went through all these conditions here. One of the things we talked about is about how biologists already had to tack on all these things to say, whoa, to make this amenable for biology, we have to have these conditions. Biological reactions don't often occur at 1 molar everything, and they often don't occur at 25 degrees Celsius, body temperature 37 degrees Celsius or 310 K. So in order for us to figure out whether or not a reaction will actually proceed spontaneously towards the products under a given set of conditions, we have to look at big delta G. So the big delta G, rather than the delta G naught prime, will tell us whether or not the reaction will actually occur spontaneously under a given set of conditions. And so in this case, so again, yes, the actual free energy change determines the spontaneity in cells. And in this case, the most important factor becomes the concentrations of the substrates and the products. So again, just to review, we can't write it out enough times. Big delta G is equal to the standard state free energy change, biological standard state free energy change, plus RT times the natural log of the products over the reactants. And so in this case, the most important factor about whether or not the reaction will proceed towards the products or the reactants is dependent on the concentrations of the products and reactants themselves. Because again, delta G naught prime is a value that's already determined because the equilibrium constant is inherent to a reaction. Now, it turns out that things can get a little bit complicated because in the cell, we're not actually at equilibrium. We're in a version of the biological steady state. Okay, why don't you guys take a minute as a group and talk about what you remember about the biological. Let's take a minute and let's come up with a definition of what we talked about the steady state one already in enzyme kinetics. What do you guys remember? Okay. Would any of the groups like to volunteer your self-appointed reporter for the day to tell me what you guys think the study, what the definition? Anybody? What does it mean in terms of enzyme? Okay, I think I saw. Right. So what that means, so with the steady state, with the steady state in enzyme kinetics, the substrate concentration was going to go down. The product concentration was going up with time. But The intermediate portion, the ES complex, the concentration did not change with time. It stayed constant. And so we're going to see a concept like this coming into play in metabolism. So if we look, so in metabolism, you have a string of enzymatic reactions, as you're going to learn very quickly with glycolysis, where the product of one reaction is the substrate of the next. So in this case, for enzyme reaction number 1, product 1 is still the substrate for reaction 2. And so what's going to happen is enzyme 2 is going to be pulling substrate 2 and making it into product 2. And so if we decrease the concentration of substrate 2 / product 1, this reaction rate is going to have to increase to try to make more product to keep the concentration of this molecule equal. So what happens here is we end up invoking Le Chatelier's principle because in the steady state, we want to keep all of these intermediates at a relatively constant concentration. So the depletion of the substrate for one reaction / the product of the previous reaction will pull the reaction before it through. And so we're going to see cases where enzymes are going to combine two different reactions together, or you're going to have one reaction is going to be pulling the next reaction through. But this is something that we're going to be seeing. So again, it's relatively steady state is when the cell has to manipulate those rates to keep the intermediates in metabolism, those concentrations relatively constant. Equilibrium is when, and there are many different definitions of equilibrium floating around out there. Equilibrium, so conditions that would satisfy equilibrium is when equilibrium. So equilibrium is when some people define it as when the substrate and product concentration are 1-to-1. I would say that's not necessarily accurate. Under some conditions, it can be the forward and the forward and the reverse reactions are equal. That's not always true. But what I think of as equilibrium is when I'm failing at defining equilibrium, but we can think of where the forward and reverse reactions have to stay relatively constant to maintain the product and reactant. You're not throwing in any energy to change that relationship, but with the steady state, the cell is constantly having to adapt and put in and take out energy to make sure that those intermediates are staying the same. Equilibrium, you could think of simply as nothing changing, but the steady state is like a duck on a pond where when you see it from afar, the duck is happy floating and it seems to just be not doing anything, but under the water, it's paddling its feet furiously to make sure that it stays afloat. That's how the steady state is. Our cell is constantly having to adapt to make sure and tweak the reaction rates of the different steps of the metabolism to make sure that those intermediate concentrations are staying relatively constant. And again, you can see here, I was struggling a little bit to come up with the right words. This is a concept that you may have to wrestle with a little bit, and that's okay. Now, enzymes are going to catalyze two classes of metabolic reactions. And when I say two classes of metabolic interactions, I have to really quick go back and give you one more definition. So we talked about the equilibrium constant, and we talked about delta G naught prime at equilibrium is equal to negative RT times the natural log of KQ. But we're going to, at any given point in time, we're going to have a ratio of product to reactant. It's just not always going to be at equilibrium. So when we have a situation where we're not at equilibrium, we can refer to the ratio of products to reactants as the Q, or the mass action ratio. So you could think of the Q as the equilibrium constant when you're not at equilibrium. And again, that's going to help us and provide us some directionality for the way a reaction will go once you correct for those conditions that deviate from standard state conditions. So now there are two classes of metabolic reactions that enzymes will catalyze, and they relate the Q to the KEQ. And I'm going to use some analogies here that will be cringy for PChemists, but for the sake of biochemistry, we're okay. And so the first type of metabolic reactions are near equilibrium. And so what I mean by near equilibrium is that the Q is close to the KEQ. So at any given point, the concentrations, the relative cell are close to what they would be at equilibrium. And so in this case, these are going to be reactions that are governed by the substrate and product concentrations. Little tweaks in the substrate and product reactions are going to have a difference on the free energy and therefore the directionality of the reaction. And we can think of these reactions as being like a pond that has a stream flowing in and out. If the pond becomes too full, it can flow in one direction. If it gets too low, you can have the stream feed into it. It's relatively easy to go back and forth here. The second type of reaction is a metabolically irreversible reaction. And so for metabolically irreversible reactions, these are reactions where the Q is really far from the KEQ. So we're going to have more than 100 times difference between the equilibrium constant and what the actual ratio of products to reactants is. And these are enzymes that have big negative big delta G's, and you'll know them when you see them. Now, these reactions, we can think of them as waterfalls. So once you have even just a little bit of substrate, it'll all go to the product because the products are just favored that much more than the substrates. Now, most enzymes in metabolism catalyze near equilibrium reactions. The vast majority of ones that we look at are going to be near equilibrium. But enzymes that catalyze metabolically irreversible reactions are very important, and they function as control or regulatory points. And they're regulated by some of the processes that we've talked about in class. They can be regulated by allostery, by covalent modifications, and I'm sure we could think of some other ways as well. And what I like to think of this, has anybody here ever been to the Whitewater Center down in Charlotte? No. Has anybody here ever been to a dam? Like with a waterfall? Okay, so I like to think about the enzymes that catalyze metabolically irreversible reactions as the control nozzle on a waterfall. So they determine whether or not the reaction can be turned on or off. But it's either all or nothing. Now, for near equilibrium reactions, generally the enzymes catalyze both reactions, both the forward and the reverse, because it's near equilibrium. Is preferred. If you tweak that just a little bit, you can change the direction of the enzyme. However, for metabolically irreversible reactions, you're going to have different enzymes for the forward and the reverse. And that's going to be fun because it's going to give you some extra. Now, what happens when we have an enzyme? When we have a reaction with if it's not favored. We're going to talk about some of the strategies that the cell can use to make enzymes that are thermodynamically not favored still happen anyway, because it's just a fact that every reaction can't be favored. And sometimes the cell has to do things that it's not easy to do. So now we're going to run through some of the strategies that our cell can use. So it turns out that free energy changes are additive. And the cell can take advantage of this, or free energy changes of successive reactions. So the cell takes advantage of this, and that it can take an unfavored reaction So in this case, we'll say we have reaction 1, which is near equilibrium. So it has a delta G that's small and greater than 0. And then we have a second reaction where we have a big negative delta G, not prime, and it's a far from equilibrium reaction. And so if we have these two reactions that come right after each other, what we can do is we can combine we can couple the reactions together. And so in this case, we have A to B and B to C. So B is going to be on both sides of that reaction, so we can cross B out, and our net reaction will be from A to C. But then it turns out we can also add together the standard state free energy changes. And so if we have one that's small and positive, one that's large and negative, we'll get a delta G not prime net that's probably smaller but still negative. And so that's how we have a reaction with a positive delta G, we can couple it with the reaction with a big negative. The big negative delta G can pull and kind of like drag that reaction through. At least I like to mentally envision it dragging. So now I've shown you how we can combine two reactions with like a very basic form. What I'd like you to do now is, here's a real reaction. You're going to see it again on Thursday because it's the first step of glycolysis, and it is the enzyme hexokinase reaction. What hexokinase has to do is it has to put a phosphate onto glucose, which is not energetically favored because it has a small positive delta G. So what it does is it couples that reaction to ATP hydrolysis. So what I would like you to do now is I'd like you to combine and write out the net reaction and then calculate what the delta G not prime would be for the net reaction. Okay, we are recording. All right. Okay, so we will go ahead and we will chant together in unison. So what is going to go on the left side of the reaction? Okay, glucose plus ATP. Are we going to see phosphate? No, because it cancels out because it's on both sides of the reaction. What about water? Same thing. Water. How about then on the left side of the equation, we're going to have, which we'll just abbreviate as G6P, and then ADP. And then if we add these two delta G naught primes together, would one of my groups like to volunteer what the net delta G naught prime would be? Yes, Maddie. Negative 16.7 kilojoules per mole. Okay, so when we couple these two reactions together, when you add a really favored reaction and a not so unfavored reaction, we can still get that free energy change. We're still releasing energy and it's favored. Now we can catalyze two reactions. And now we can also help catalyze a reaction that wouldn't have been favored on its own. So now, let's say that we're hanging out in the cell, all right? And we want to figure out what the big delta G is. From the delta G naught prime, we know that under standard state conditions, this reaction would proceed towards the products. But what about under these conditions? And then let's say we are at 310K. Let's say we're at body temperature, so 37 degrees Celsius or 310K. I'd like you to calculate what the big delta G would be under these conditions. And I would start by writing out the equation relating delta G and delta G naught prime. Does everyone have done the conditions? Okay, I'm going to temporarily stop projecting. Okay, all right. So let's see. So would one of my groups like to report their answer for the delta G for this reaction? I guess I could have had you all written them on the board. Okay, Keegan, I saw your hand first. Okay, does anyone disagree with an answer in the neighborhood of negative 10.8? I'm going to show you how I arrived at negative 10.8. All right. And again, as always, this video will be posted so you can walk back through it if necessary. So the big delta G is equal to the standard state delta G, not prime, which you've just calculated, plus RT times the natural log of the concentrations of the products, which if we look at this reaction here, it's ADP and G6P over the reactants, which is glucose and ATP. So that's 5 times 3, or 5 times 3 over 1 times 1.5. So it's negative 16.7 plus 310 K is the temperature times the times R, the gas constant. By the way, this is in joules, so you're going to have to convert it to kilojoules per mole K times the natural log of 15 over 1.5. We calculate this, we convert it to kilojoules, and we get 5.9 kilojoules per mole. We add that to negative 16.7 for a net delta G of negative 10.8 kilojoules per mole. Does anybody have any questions on my logic for this calculation? Good? Okay. As always, if something comes up, you can ask me after class. I'm more than happy. Now, there was one way that enzymes can help make enzymes can also use energy-rich compounds to drive unfavorable reactions. And we're going to see 3 examples today. We're going to talk about phosphoryl-containing compounds, the epitome of the phosphoryl-containing compound we've already seen in nucleic acids. They can use thioesters, which are basically the sulfur version of the phosphoryl-containing compounds. And then finally, we can see reduced coenzymes. And with the reduced coenzymes, we're going to talk about a different type of reaction, which is super exciting. Okay? All right, so the first, the phosphoryl compound is, again, a molecule that we've already seen, which is adenosine triphosphate, or ATP. So I have the structure of ATP here. Some of you were asking about when you're drawing out nucleotides, if you have to draw the hydrogens on the ring. I say if you want to do implied hydrogens on the ring for the purpose of nucleic acids, that's fine. But one thing I will point out is that adenosine triphosphate is ATP, not DATP, so it is a ribonucleotide. So it's going to have a 2' hydroxyl as well as a 3' hydroxyl. So just an FYI, if you're drawing out ATP for a reaction, don't forget both of the hydroxyls. Now, a tour of ATP, it has the ribonucleotide, it has the nucleotide, it has the ribose ring, and then it has 3 phosphates that are covalently linked together. And then these 3 phosphates is where the energy comes into play. So we can refer to the bonds that are between phosphate, okay, so this is alpha, beta, and gamma. We can refer to the bonds between alpha and beta and gamma as phosphoanhydrides bonds, because those groups as phosphoanhydrides, whereas this group here is a phosphoester because it's connected to a carbon instead of another phosphate. Now, turns out that ATP has this really huge negative delta G naught prime. So under standard conditions, if we look at turning ATP into ADP or AMP, we have delta G naught primes of like negative 30, negative 32 kilojoules per mole. That is a far from equilibrium reaction. A big delta G naught prime. Okay? And this big delta G naught prime largely comes from the fact that breaking up ATP either into ADP or AMP is very exothermic. And now we're going to walk through the reasons why ATP hydrolysis is so favorable. Some of these may be familiar to you already. And the first is that when we pluck off that alpha phosphate, we're actually minimizing electrostatic repulsion. So if we look at ATP, we have 4 negative charges on 3 phosphates. When you hydrolyze that last phosphate, you end up with 2 negative charges on 2 phosphates. So you're minimizing electrostatic repulsion. So that's really favorable. The next thing, and the next consideration is that the products are more stable. So if we look at the phosphate, and then particularly the phosphate, but also the ADP, when you take out that last phosphate, it's very stabilized. And so it's able to delocalize that electron density more than when it was part of ATP, when it was part of ATP. So that resonance stabilization leads to making it favorable to hack that phosphate off. And then finally, the ionization of ADP. So when ADP is formed, it has a proton on that terminal oxygen. When that proton comes off, that's a really favorable reaction. And so when you hydrolyze ATP, you have that potential for ionizing ADP. That also makes the production of ADP favorable. So there's the three reasons why we get this huge for ATP to hydrolyze it, and why, for instance, we can use it to catalyze putting a phosphate onto glucose, because it has that, because of all those things that cause it to be structurally favored. Now, enzymes that catalyze a phosphate transfer, and very often a phosphate transfer from ATP or another nucleotide, are called kinases. Would anybody like to venture a guess? There's a very definitive hint on the slide. It's taking a phosphate group from yes. Yes, very good, Addie. Kinases are transferases, because they're transferring a phosphate from a nucleotide to another molecule. So there are three examples here. I'm not necessarily going to walk through them individually in the interest of time, but you can see different examples where an enzyme will swap. And so, for instance, forming GTP to GDP, so you start with one monophosphate and one triphosphate, and you end up with two diphosphates. And adenylate kinase is one that we see during oxidative phosphorylation. But either way, what we're doing here is by transferring, we're forming high energy phosphate bonds that can be broken later to release energy that can fuel an unfavorable reaction. And so our bodies will use kinases to strategically move phosphates when we have the energy to do so then we can use that energy later. And so one particular example is nucleoside diphosphate kinase, which was the second example on this slide. And this is an enzyme that transfers a phosphate from ATP to another nucleoside. Now, this is a ping pong mechanism. We talked about, I think I mentioned when we talked about chymotrypsin, but just to hammer it in again, the ping pong mechanism is when you have one substrate go in and leave, and then you have substrate 2 go in and leave after. So you have two substrates, but they don't get operated on at the same time. And that's when we have a reaction like this, we have a diagram where we can have one substrate flowing in and out, and the next substrate flowing in and out. So what happens here is ATP comes in, and that phosphate gets covalently attached to a histidine on the enzyme. So this is an example of covalent catalysis, where the phosphate is temporarily going onto the histidine. ADP is like, oh, I transferred my phosphate, I'm off now, okay, bye. And so it leaves. Then another nucleoside that needs a phosphate comes in, and then that histidine transfers the phosphate onto the end of that nucleoside. And now it has 3 phosphates instead of 2, and then that phosphate can be transferred or hydrolyzed somewhere else. And so again, our body can shuffle around these phosphates to have energy available when we need it. And just another way of thinking about this is if we have an energy diagram, for instance, of a phosphoryl group transfer. So let's say, in metabolism, we're going to see instances of where and then when that phosphate is taken off of that group, that's a really high energy bond. So we're talking about how the hydrolysis of ATP is negative 30 kilojoules. it releases so much energy because the products are so much more stable than the reactants. So ADP plus PI is so much happier than ATP that it releases a lot of energy when you break that bond. But during metabolism, we're going to see our body transferring phosphates to make molecules that have phosphate oxygen bonds that are even more unstable or more energy containing than ATP. And what that does is that allows the body to then donate that phosphate to make ATP. That's called substrate phosphorylation. You don't have to worry about that now. We'll point it out during metabolism, but we're going to see our body is going to tack a phosphate on, manipulate it, and make a molecule that's so high energy that we can actually get ATP out of it. So there we go. Now, the next type of molecules that our body uses are thioesters. And these are analogous to ATP, those esters, but they have an S instead of an oxygen. And so the big thioester that we're going to see in metabolism is acetyl-CoA. And again, the hydrolysis of acetyl-CoA has a delta G, not prime, in the same neighborhood as ATP hydrolysis, which makes sense. Now, the last type of reaction that we're going to talk about today is that another way that we can catalyze unfavorable reactions is using energy transfer through the flow of electrons. And specifically, the flow of electrons does the work or produces the delta G. And so oftentimes, we will see this with the oxidation of the building blocks that make up the molecules in our body are going to be coupled to a reduction. And so the types of biological enzyme oxidizing agents that we're going to see are coenzymes that we've seen before. So NAD or NADP+, FAD+, or FMN, and then Q. Now this is not Q, the reaction quotient Q. This is coenzyme Q. But you can just forget about coenzyme Q until we get to the electron transport chain and oxidative phosphorylation. We're not quite there yet. So how are electrons transferred? There are 4 different ways that we're going to see electrons transfer. The first is they can be directly transferred between 2 atoms. So in the case of these iron and copper atoms. Electrons can be transferred as a hydrogen atom. So a hydrogen plus a proton plus an electron. Or we can even see them as a hydride. So where we have a hydrogen with 2 electrons, or an H-. And then finally, the last way that we'll see is that we can see the electrons transferred directly to oxygen, which is the ultimate electron acceptor. So to get some practice with writing out these reactions, all oxidation reduction reactions can be written out as half reactions. And so in this case, 1/2 reaction is going from Fe2+ to Fe3+, and the other is from copper 2+ to copper+. So we can write this out as Fe2+, Fe3+, Cu2+ to Cu+. I guess we can write that as equilibrium. Now, what I'd like you guys to do is take a quick minute and decide, if you look at these 2 half reactions, which half reaction and which half reaction, which atom is oxidized and which is being Okay, which atom is being oxidized? Yes, Elena. The iron is being oxidized. And why would you say that the iron is being oxidized? That's okay. So it's going from 2 plus to 3 plus. And when it becomes more positive, it's losing an electron. So the enzyme that loses an electron is being oxidized. On the other half reaction, we see copper going from 2 plus to 1 plus. This means it's being reduced or it gains an electron. So for an oxidation reaction, one atom is going to lose an electron and transfer to the other atom to gain an electron. Yes. So when, oh, that's a good point. Okay. So I guess that this would be Cu2 plus, oh, okay. We're not going to go there. So we're not going to go there. So you'll have a table, and we're going to practice that, where it'll help you account for the electrons. Right now, I'm just drawing out the, I guess perhaps it would be Cu2 plus E minus and Fe3 plus E minus. But we'll do another example of that when we practice a problem. So the reduction potential is tells us how badly does a molecule want to receive or donate an electron. The reduction potential, we write it as E, not prime. And if it's positive, it's more likely to receive an electron. And if it's negative, it's more likely to donate an electron. And so these values are all relative to hydrogen. So all of these molecules are going to be done, all those values are done relative to the reduction of hydrogen. And so we can measure the potential difference between a reaction in reference to hydrogen, and the measured potential difference is the electron motive force, or the EMF. And then we can get the E naught prime, or the reduction potential, and that tells us the degree to which the molecule wants to be reduced. So if we look at a series of biological half reactions, and so this is what you'll be given on an exam. So I wrote in the electrons here for iron and copper. If we look at biological half reactions, if you're asked to do this on an exam, you will be given a table from which you can work. And so if you want, so you'll notice that each of these half reactions, they're all written as reductions. So for all of these, you're going to see the electron on the left-hand side of the reaction for the reduction. This is going to be so this is written in terms of a reduction. And so we said that oxygen is the ultimate electron acceptor. It has the most positive the most positive electron reduction potential. We have hydrogen coming in at 0. And then all of these guys down here with negative values will be less likely to receive, less prone to receive an electron than hydrogen would. Now, if we were looking at an oxidation potential, it would be the negative of the reduction potential. But we write all of these reactions in terms of reduction potential, and go over the protocol for how you would treat these when you're determining the delta E of a reaction. So in the interest of time, I'm going to give you a brief, okay, so the way then that we would calculate the free energy change for a reaction, so if we have an electron transfer, whether or not it's going to be favored towards the products or the reactions, we're going to get yet another equation for delta G naught prime. So for an electron, so for an oxidation reduction reaction, the delta G naught prime is going to be equal to negative NF delta E, where N is the number of electrons, F asperity is constant, the value is here, and delta E is equal to the reduction potential of the electron acceptor. So this is the molecule that gets reduced, and the E naught prime of the electron donor, or the molecule that gets oxidized. Now, when you're going to your table and you're practicing and you look at this table, you're going to want to go and go, oh, I should switch the sign of that because it's of the donor because it's being oxidized. Do not do that. You would have to, when you're doing this reaction, always is going to be easier if you always use the reduction potentials, even if the reaction that's happening as an oxidation. And you'll see why when you work out this problem, when you work out a problem. And then finally, if we want to know the big delta E of the reaction, which can indicate the spontaneity analogously to the big delta G, we would take the delta E naught prime plus some constants times the natural log of the acceptors over the donors. This is just an FYI. We didn't talk about chapter 11, but this is the same principle that determines the free energy of transport for ions across a membrane. This is a really quick look at the molecules that catalyze this. I'm not going to go into a whole lot of detail now, but here's a flavin adenine dinucleotide. The chemistry occurs on the 3-ring part, and it occurs by transferring one hydrogen atom at a time. The one that we're going to see a lot is NAD. When we do reactions that use NAD, you will need to know the structure of the business end of the nicotinamide ring of NAD, but we will go over this reaction when we actually have a mechanism where we use NAD. Here are some values for the constants to help you. And lastly, I want to close on starting to put some of these values to use. So what I want you to do is I want you to look at the reduction of FAD by NADH standard state. So start by writing out the net reaction, bust it into the half reactions. You'll figure out what's being reduced and oxidized, and then calculate the delta E naught prime and the delta G. Yes, okay. Sure. Okay. Put the table on the board. Okay. Oh, yes, of course. Here we go. Okay. So if we're looking at the reduction of FAD by NADH, okay, FAD by NADH, okay. So what this means is that FAD is being reduced. So we're going to go from FAD, which is the oxidized. So if we look here, FAD is the oxidized, and FADH2 is the reduced, because it's had electrons transferred to it from somewhere else. If we look at NAD, NAD plus is the oxidized form, and NADH is the reduced form. So we're going to be starting with the reduced form of NADH, and then we're going to end with the oxidized form NAD plus. And then there's going to be actually another proton on that form side to help with the accounting. Okay, Does that help get everyone in the right direction? Okay. Okay, so FAD is being reduced to FADH2 because we're starting off with FAD over here in its oxidized form. It'll get one hydrogen transferred and then another hydrogen transferred to become FADH2. Now, FADH2 is right here. FAD, the reduction of FAD plus 2 protons plus 2 electrons to form FADH2 here. If we look at the reduction of NAD, it's down here. Now, as long as the molecule that's being reduced is higher up on this table than the molecule that's being oxidized, you're okay. So the half reaction for FAD being reduced would be exactly this reaction here. The half reaction for NADH being oxidized to NAD plus would be this reaction here, but flipped. It would be flipped. That's how you would write it out. Now, when you would go to calculate the delta E for this reaction, and I know it's technically 1030, if you look at the delta E, you would do the E of FADH2 or FAD 2 FADH2 minus the E of NADH to NAD+. Now, because you have a minus there, you're accounting for the fact that this reaction is as it proceeds in the table, and then this reaction is flipped to what it would be in the table. So that's why I encourage you to just plug the values from the table into this equation rather than trying to flip-flop the signs, because this is how it will work out. Okay, so what I'm going to do is I'm going to have you guys do this on your own time, and I will post a key for how you would solve this problem and then how you would solve the next problem. You will know how to do this, so you're more than welcome to ask me questions before or after class or during our study session, but I will post the key so you can check your answers against the practice problems.